Mm. Mm. Hey, Danielle. Feel free to ask questions if you have any.
Okay, thank you. Wait, okay. Question. Is the face-to-face test it opens next Wednesday, right?
As a bare minimum, it'll open by next Wednesday. It's just I'll probably even open it before that.
So is it open for a week? So like this upcoming, was it the 29th through
Yes, it'll definitely be open for like a whole week or at least, 5 or 6 days. But if you need a whole week, I can make sure that happens too.
Okay, and if I have the same proctor, do I need her to text you again?
No, it's not. That's all taken care of. If she's willing to do it again, all I have to do is just get a text message from her saying she's doing it, and I'll send her a password.
Okay, that sounds good. Thank you so much.
You're welcome. Got about 3 minutes, everybody. Feel free to ask me questions or to go ahead and chat me your first and last name. I see one of you already did. Thanks, Carter. Remember, since you are chatting me your actual first and last name, you can feel free to change your username for whatever pops up on the screen. So no one will know who you are. You can at least change it to your first name or something like that. All right, about time. I guess we better get started. So, the last time we talked, we were working on electric potential from chapter 23. We got a couple more examples left in there. In fact, uh, got caught in the middle of example 23.4. Specifically, I'd calculated the electric potential V at all points R, which is a distance from the center of a charge, basically a solid charge sphere of radius r0 and total charge q centered on the origin. And I was able to compute that. And of course, you can check the notes. But the last thing I wanted to do with that was give you an actual graph of what that electric potential looked like as a function of r. As a function of r. So far, I've only had two of you guys chat me your first and last name. So go ahead and do that. I'm going to go ahead and share my iPad with you, and you'll see a sentence introduction what we're doing. But anyways, here I go. So the screen should come up any minute now. So what I had found, it says right here, it says last time we computed the electric potential at all distances r from the center of a solid conducting sphere of radius r0, charge q, and centered on the origin of coordinates. What we actually found, by the way, was v of r is equal to, it was a little bit odd, but basically I'll make it like a piecewise function. It was equal to q over 4 pi epsilon naught r for r greater than or equal to r0. In fact, it came down to just r0, q over 4 pi epsilon naught r0 at the surface. And then it was q over 4 pi epsilon naught r0 for r less than r0. So as a actual plot, as a function of r, what this looks like is right here. You can say, let's say this is r0, and basically the potential was a constant, let's say q over 4 pi epsilon naught r0 all here. So the graph looked like that. And then at r0, it fell off like 1 over r. Not 1 over r squared, but 1 over r, like that. So that was the solid conducting sphere. Now remember, that's partly because as a conductor, it cannot have any electric field inside of it. In the electric field inside the conductor, and since there's no electric field inside the conductor, we could take a Gaussian surface and enclose it just inside of the outer edge, all the way along the inside, like keep it like a micrometer. In fact, you could literally go as close to the edge whose radius is r equals r0. You can get as close to that as you want. And if you feel like you need to go closer, you can do it again and go closer. But just put a little sphere on the inside of the actual conducting sphere, and just inside of that inside, since the electric field's zero inside, the flux on Gauss's law would be zero. So the left-hand side of Gauss's law would be zero. And that means the charge, that means the charge inside would be zero. That actually gave us the concept that all the charge on a conducting sphere will reside on its outer surface. And of course, that's also consistent with the electric field being zero inside of it. And that allowed basically the voltage not to change at all once we got to the surface. And that's also consistent with the idea of a conducting surface being a equal potential surface. So in this case, it's not only the surface of a conductor, it's the whole body of the conductor. All of it's at one equal potential. If it wasn't, again, if you had one part of the sphere has a different electric potential than another part of the sphere, then it would obviously have a high electric potential at one point and a lower electric potential at another point, and that would force charges to move from the high potential, positive charges, to move from the high potential to the low potential, and that's the antithesis of electrostatics, like I said, that we are actually studying. So electrostatics meaning there's no free charges to roam around. They're not actually roaming around, let's put it that way. There are free charges, that's what conductors are, but they're not roaming around. Any questions on that last example? So that one was example 7 dash or 23 dash 4. Now we have another example, and this is example 23 dash 5. But before we start that, does anyone have any questions before I go on? I wanted to make sure I did that graph, like I said, just because I didn't get to finish it last time because I wasn't paying attention to the clock as well as I should. And the time had creeped up on me, so I felt bad about sticking y'all with a late class and all that good stuff. But anyways, anybody have any questions? Okay, so that looks like everybody's good on that. So regarding this next example, it's telling us that when an extremely high electric field is in place, let's say in our atmosphere actually becomes a conducting surface, a conducting substance. Specifically, what happens if the electric field reaches a voltage of 3 million volts per meter? What that means is literally that the electric field uh, has a strength of 3 million volts, uh, and that change in voltage at 3 million volts happens over a distance of just 1 meter. Okay. So for instance, air, which actually conducts at that, means that if you get within 1 meter, let's say, of ground and the voltage is 3 million volts, then you definitely will get lightning striking running from well, if you're thinking about it as positive charges, it would run from the positive side to the low voltage side. In reality, of course, a lot of what we do is electrons moving, but the main thing is that voltage difference of 3 million volts would allow a lightning strike to travel a distance of 1 meter. And because of that, they're asking you to express specifically how the voltage is related to the electric field. And then they wanted us to show specifically that the electric field, or excuse me, that the voltage is proportional to the radius. So let me read the question specifically. And like I said, this is an example 23.5. It says when very high voltages, when Harry Vi when very high voltages are present, air can become ionized due to the high electric fields. Any free electrons in the air produced by cosmic rays, for example, can be accelerated to sufficient kinetic energy to knock electrons out of the O2 and N2 molecules of the air. The air then becomes conducting, and the high voltage cannot be maintained as charge flows. This breakdown of air occurs when the electric field exceeds about 3 million volts per meter, and we call that E sub BD. So I'm going to write that down right quick. E BD is the electric field strength at which air breaks down, and it is approximately 3 times 10 to the 6 volts per meter. They want us to show that the breakdown voltage VBD for a spherical conductor in air is proportional to the radius of the sphere. So A, show that VBD for a sphere or let's say spherical conductor is proportional to the radius of the sphere. And then B, they want us to estimate the breakdown voltage in air for a sphere of diameter 1 centimeter. So estimate VBD in air for a sphere of radius equal to 1.0 centimeter. Okay, so that's our problem. Here's our solution. What we do know is the voltage created by a conducting sphere of radius r is specifically given by V is equal to Q over 4 pi epsilon naught r. And we also know the electric field E for that same sphere is Q over 4 pi epsilon naught r squared. And we ideally wish this to be equal to E breakdown. So just looking at these, you can see that if I take E breakdown, which equals 3 times 10 to the 6 volts per meter, but also happens to equal Q over 4 pi epsilon naught r squared. If I look at that and then realize that if I take EBD and multiply it by R, somebody just came in, let me let them in. If I take that EBD and multiply it by R, then I get Q over 4 pi epsilon naught r squared times r, which equals Q over 4 pi epsilon naught times r, because of course this r cancels out with that exponent of 2 and just leaves the r in the bottom. But Q over 4 pi epsilon naught is just V breakdown. Therefore, we have V breakdown is equal to R times E breakdown. And QED, so it's been shown. Okay, so that was part A. Now part B, and I'll go ahead and circle this. Part B is for us to estimate the breakdown voltage for a sphere of radius 1 centimeter. What I want you to look at, though, is VBD equals R times EBD. Just basically means that for a really small radius R, that number is going to be multiplied by 3 times 10 to the 6 volts per meter. And for instance, if it's 10 to the negative 2, then we all of a sudden are looking at not 3 million volts per meter, but all of a sudden we're looking at 30,000 volts per meter. And that means a low breakdown voltage occurs if you have a low radius. That is the essence of a lightning rod. A lightning rod is basically a rod that sticks up and the tip of it comes down to a point. And of course, coming down to a point is essentially saying it's a really small sphere. So what it does is it allows a much lower electric potential difference between the air and the lightning rod before the breakdown occurs, so that you can actually fetch lightning more or less. So basically, because the voltage is so low and the thunderclouds, for instance, as your book said, was about 10 million, or excuse me, 100 million volts per meter as the electric field for that. And therefore, if you have a very low voltage that's allowed between it, it's not hard for it to get it. And in fact, it'll get that breakdown voltage will usually be reached well before you reach that much higher electric field strength. And what will happen is lightning will strike the lightning rod, and the lightning rod should, of course, be wired very robustly to the actual ground of the earth. Like literally, it's not uncommon to see some old lightning rods connected by, I would say, probably half-inch thick iron rods is what I've seen running. They were looked like a wire, but it was square and it was twirled like that. So it had been twisted and it was twisted all the way down the roof. And then it came around like the gutter and the overhang and then went straight down to the ground where it was connected to a ground. Modern day electricians basically will connect your house to a ground. For instance, for all the little circles in your light receptacles, that's where ground is connected to, and it basically runs a wire out to a long metal rod that's covered in copper. I think it's copper plated, not solid copper, obviously, but it's usually 6 or 8 feet long, and it's just banged straight into the ground right below your circuit panel, and that's the ground. But something like that is what you need to safely shuttle the lightning bolt away from the house without causing any problems. But again, you also fetched it at a much lower voltage, so the lightning should be a little less severe too. Now, to estimate what the breakdown voltage would be for a 1 centimeter radius sphere, we're going to write VBD is equal to 1.0 times 10 to the negative 2 meters, because that's what 1 centimeter is in meters. And then we're going to multiply that by 3 times 10 to the 6 volts per meter. And that gives me, of course, 30,000 volts. Okay, again, there's really no sig figs but one in here, so I have to underline them all, but that's basically the result. Anybody have any questions on that? All right, so yeah, that's a really, really easy way of looking at it. I remembered in my graduate level electrodynamics course, we spent, it was at least a week, but I want to say it was a week and a half or 2 weeks, meeting 2 days a week, of course. I can't remember if we spent 3 whole days on it or 4 whole days on it, but we spent it all on solving the problem of basically a lightning rod. But in that case, we started with a sphere with a little slice out of it, and then we imagined the slice getting so big that the sphere became just a little tip like a lightning rod. And doing that analysis, like I said, took us some long period of time. It was just basically a solution of a differential equation. So, anyways, that version that y'all had is a lot easier way of showing it. But now you see the smaller the radius, the smaller the breakdown voltage, and the smaller the breakdown voltage, the easier it is for lightning to jump. That's exactly why, for instance, during the winter, if you scuff your feet on the carpet and you go to grab your door of your bedroom or your door of the living room or something like that, you're liable to get a shock because, again, that spherical doorknob is a fairly small radius. The 3 million volts per meter is, a good sized number, but lo and behold, you scuffing your feet on the carpet manages usually to steal a bunch of electrons from the carpet. You'd be surprised at how many. Then you're have a net negative charge, and that causes the electrons in the actual doorknob to run away because you're negatively charged, and all of a sudden the doorknob looks positively charged. And the next thing is when your hand comes close to it, your hands are negatively charged, and the doorknob looks positively charged, and that creates a voltage difference between the tips of your fingers and the knob, and therefore lightning will strike and jump across there. Sometimes you even feel a little bit of pain. So that's how that works. Anybody have any questions? Okay, so we now have, based on, for instance, that last example, 23.5, we know how the voltage due to a point charge behaves. So I'm going to go ahead and block this off so we know that's the end of that example. And I'm just going to say that the voltage, well, I'll just say a point charge establishes a voltage field. Oh, crap. So we are using the phrase, remember I said aura originally to talk about the idea of an electric field. Now I'm talking about a scalar field. And now that we have cemented in you some kind of idea that a field is like an aura, I'm just going to use the phrase field. And around a point charge, you're going to have a field given by the electric potential. So this is going to establish a voltage field V. Dang it, there it goes again. V of R, where R is the distance from the center, is equal to Q, the charge of the sphere of the point charge, over 4 pi epsilon naught R. Okay, so that's the actual voltage field. And in fact, if you wanted to assume it's infinitesimal and you wanted to find it, kind of compute what the total voltage would be from a series of them, then you can come up with a more general phrase that allows you to build any kind of shape and then calculate the aura that that shape of charges works. In that case, we get V is equal to 1 over 4 pi epsilon naught times the integral of dq over r, where we can say dq over dl is equal to lambda, dq over dA is equal to sigma, r dq over dV, that's volume, and A was area, by the way, is equal to rho. Or alternatively, you can write that dq is going to equal lambda dl r sigma dA r rho dV. So that's our big conclusion there. Now that we have that, we can go about solving problems with distribution of charges. So instead of imagining just either point particles are exactly spherically symmetric charges, we can now imagine any kind of shape and just build it up as if they're made up of infinitesimal point charges. We know that's not really what exists. They're made up of atoms, which are really, really small, but technically speaking, not zero size. But it turns out that this actually gives very accurate results, at least on the scales that we're working with them. So before I do that, let me work another example. And this one's kind of a nice, straightforward example of some of the simpler problems you have to be able to solve. So we know, for instance, that there's an actual relationship. There's an actual relationship between potential energy and electric potential. Specifically, what we found was the change in potential energy, delta U, darn it, the change in potential energy, delta U, is equal to Q times the change in electric potential, delta V. Remember, that was where the idea of the electron volt came from. So now we have a question, and it's going to be like this. Let's say, example 23-6. Again, this is just like the book's example. It says, what minimum work must be done by an external force to bring a charge Q equals 3 microcoulombs from a great distance away, take R equals infinity, to a point 0.500 meters from a charge capital Q equals 20.0 microcoulomb. So what we're asking is what minimum work is required to bring a Q equal, I'm going to say 5.00 microcoulomb. Notice I'm making up sort of my own problem. To bring a Q equal 5.00 microcoulomb from R approaching infinity to R equals 0.750 meters, so 75 centimeters basically. uh, from a Q equals 30.0 microcoulomb spherical charge. Whoa. R point charge. And the point charge is a little easier because remember, for a spherical charge, if it had a radius, let's say R0, then the formula V equals Q over 4 pi epsilon naught R works as if it's a point charge at the origin, but you can't get closer than R equals R0, because if you got closer than that, you'd actually be inside of the spherical charge distribution, and you'd have to do some work to compute what fraction of the charge is inside in a smaller radius than the location you're at, and what part's outside of it, and therefore what's the electric field there. So we're just avoiding that. So I will draw the diagram, giving you some idea of what we're looking at. I'm going to use the straighten line drawer, so that makes it kind of nice for me. And what we have here is an x-axis, a y-axis, and a z-axis. And I didn't really have to show all that. It's just a matter of I wanted to put the spherical charge at the origin like so. Whoop, that was terrible. Take that off too. Come on, get off there. And there's our spherical charge of radius, some radius smaller than R, of course. And what we're going to do is imagine that some distance away from the center, for starters, let's go ahead and move this sphere, because it seems like I screwed that sphere up just a little bit by getting it a little bit off center. I'm going to try to make it a little better centered. That's cool. Okay, now I'm going to draw a dashed line like this, and I'm going to show a apparent break in the dash line. And then now we're all the way out at infinity. And what I'm imagining is a little charge Q being brought in all the way to right here, which is a distance equal to R. Okay. So that's what we're trying to figure out. And what we want to know is what work was done. So if I can calculate the electric potential energy that the charged little q would have at that point, then the electric potential energy is exactly equal to the work done in bringing it against the force of nature. Because notice these are both positive charges. I got a 30 microcoulomb and a 5 microcoulomb charge. They're both positive. The electric coulomb force is actually forcing them apart or trying to repel. So it's going to take a certain amount of work against the conservative force to move it from Q equal or from R equals infinity all the way to R equals 0.750 meters. That's exactly how we define the potential, or the potential energy was delta U is equal to the negative of the work done. In this case, I'm just going to take the magnitude of it and say that that's going to be the work done. So what I can use is the following solution. That's going to require V to equal Q over 4 pi epsilon naught R. That's the electric potential energy per unit charge, i.e. the voltage that the charge Q of causes. Okay. And then the potential energy change, delta U, is equal to the charge times the change in voltage. Okay. So if I actually take the change in voltage from R equals infinity to R equals big R, I know the result is just plain R, because that's how we derive the formula V equals Q over 4 pi epsilon naught. So I can immediately say delta V is just equal to Q over 4 pi epsilon naught R. And that's equal, of course, to 30.0 times 10 to the negative 6 coulombs divided by 4 times pi times 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. And then at that specific distance, which would be 0.75 meters, we can see now that we should have 3 sig figs for everything. And I get that the electric potential, notice I said electric potential, not electric potential energy. The electric potential is 30, 10 to the negative 6 divided by parentheses 4 times 3.14159 times 8.85 10 to the negative 12 times 0.750 close parentheses. That gives me a voltage of 3.60 no 3.597. That's one extra sig fig. 3.597 times 10 to the 5th, and that's volts. And double checking that. Yep. So that's basically 300,000 volts is the electric potential difference between infinity and 0.750 meters. So now I can say work equals delta U. I'm going to say at least in magnitude. In this case, it's going to be Q times delta V. And the Q, of course, is 5.00 times 10 to the negative 6 coulombs times the delta V, which is 3.597 times 10 to the 5th volts. And remember, a volt is a joule per coulomb. So when I multiply that by the coulomb, I just get joules. So I'm taking my answer for the voltage and I'm multiplying it by 5 times 10 to the negative 6. And that gives me 1.799 times 10. That's actually just 1.799 joules. Whoa. So that's the actual work done in bringing the charge little q from infinity into a distance of 0.750 meters from the 30 microcoulomb charge. Anybody have any questions on that one? Okay. Well, there's another one we should work before I go on to doing that integration stuff. And this is very much like the 4-part series that I did earlier this semester. Remember, I took time to calculate the force on charges directly above the center of an electric dipole, and then directly above the, I think I did the right above the negative charge. I might have did right above the positive charge. I can't remember. But the main thing is I did it above one of the charges as well as directly above the middle of an electric dipole, and I calculated the force in obviously both of those 2 different ways. In one case, I did it by calculating the force directly with Coulomb's law of force, and that gave me 2 of the 4 videos. And then I did it again using electric field first, calculating the electric field at those points directly above the middle and directly above one of the charges, and then multiplied that by Q to get the force. And that showed, of course, that both ways were equivalent. So now we're going to do another one where I'm going to work it for a dipole, and you're going to see how much easier it is when working with electric potential as opposed to electric fields or forces. So this one's going to be example 23.7. So with example 23-7, we want to know, calculate the electric potential at points A and B in the figure below. Okay, so that's our problem. Now, what I'm going to do is draw the actual dipole, the electric dipole, and I'm going to draw it in a coordinate system so that we can already be ready to start working. My coordinate system I'm going to use is this and this. So this is my x-axis. This is my y-axis. And then over here, let's see, I'll go 1, 2, 3, 4, 5. I'm going to go 5 blocks to the right. And right there, I'm going to put a charge of Q1 is equal to positive 50. I think I'm going to do a different one. Let's do positive 10.0 microcoulombs. And then over here at a distance of 5 units away, I'm going to do Q2 is equal to negative 10.0 microcoulombs. And what I'd like to do is go up a distance of 30 centimeters. Actually, I shouldn't put it there. I don't have enough room, so I'm going to put it over here on the right-hand side instead to show how far up that distance is. This distance right here is going to be 30.0 centimeters. This distance right here is going to be basically the x coordinate is basically going to be 45.0 centimeters, and this distance over here would be negative 45.0 centimeters. Okay, now my points are going to be right here, and I'm going to call this point B, and then right here is point A. So I want to know the electric potential at point A and point B, and here goes my solution. So the solution is going to require that we know the formula for the electric potential established by a point charge. That electric potential formula is V equals Q over 4 pi epsilon naught R. That is a scalar quantity, so that makes a really big difference. I will also, well, I'll go ahead and draw that in later, but let's go ahead and do part A. So for part A, the voltage at A is equal to the voltage at A due to the minus charge plus the voltage at A due to the positive charge. So I'm going to write it that way. So now I can say voltage at A is equal to, now the distance between A and the negative charge Q2, we can see is just 30 centimeters. So that's not too terrible of a difficult thing to do. But what we're going to have is this is going to be Q2 over 4 pi epsilon naught, and then 0.300 meters is the distance. And then we also have to do it for Q1. So that's going to be Q1 over 4 pi epsilon naught times. Now, in this case, the distance is all the way over here. Okay, we can see that that distance would be equal to the square root of 90.0 centimeters squared plus 30 centimeters squared square root. So we know that's what's going to happen. I can go ahead and put that in here as 0.900 meters squared. I'll put a square root right there, plus 0.300 meters squared. And then I finish the square root like that. And that should give me the answer. I'm going to write it down below because I obviously ran out of space by writing that long thing. So this is going to become Q2, which is negative, oops, he don't does this, negative 10.0 times 10 to the negative 6 coulombs over 4 times pi times 8.85 times 10 to the negative 12th coulombs squared per Newton meter squared times 0.300 meters, plus this one's going to be positive 10.0 times 10 to the negative 6 coulombs over 4 pi times 8.85 times 10 to the negative 12th coulombs squared per Newton meter squared. Now, when I actually do that square root, what I'm actually going to get is the square root 0.9 squared plus 0.3 squared. That gives me 0.9486. 868 meters. So I've given you way more digits than really necessary. I gave you 2 extra sig figs there, or 2 extra digits beyond sig figs there. Now I can do the calculation. If you'll notice, the easiest way to do this calculation is recognizing that both terms have the 10 microcoulombs, the 4, the pi, and the 8.85. So I'm going to break it up that way. So I'm going to say 10 times 10 to the negative 6 divided by parentheses 4 times 3.14159 times 8.85 times 10 to the negative 12th, close parentheses. That's the thing that they have in common, and that's 8.99 or 8,900 or 89,918. So 89,918. And that unit turns out to be, notice that's got everything in it except for the meters in the bottom. So this should come out to volts per meter. So I'm going to call that volts per meter, and I'm going to recognize that the 1 and the 8 are not sig figs there. And now all I have left is I'm going to reverse the order of these because I don't like leading with a negative. So it's going to be 1 over 0.94868. Oh, it's actually volts times meters, not volts over meters. So let me fix that right quick. So this is going to be volts times meters, not volts per meter. Now the other one's going to be negative, and it'll be 1 over 0.300 like that. And now you should see that this is one and the same thing. So what I'm going to do is I'm going to take the number that I just got, the 89,918 and some change, and I'm going to multiply that by parenthesis 0.94868 raised to the negative 1 power plus or minus, excuse me, minus 0.3 raised to the negative 1 power, close parentheses, and that gives me negative 2.049 times 10 to the 5th volts. So that's our voltage for V at A. Anybody have any questions on that? Or hopefully y'all are verifying my calculations, making sure you're getting the same thing. No questions? All right, let's go ahead and do part B. You actually see a really nice simplification here. So for B, hopefully I've already seen it. We have the velocity at B, or excuse me, the velocity. The voltage at B is equal to the voltage at B caused by the negative one plus the voltage at B caused by the positive one, which I think you can see is going to be equal to, again, we're going to have the same, we'll actually have that same whole front stuff out in front. So it's going to be 89,918 volts times meters with two extra sig figs. That's just to account for, let me show you what I'm actually doing. That's just to account for this part of the number that appears in both of them. Notice the difference being that the charge in one case is positive and the charge in the other case is negative. So that's just that part. Now what you're going to see is that is all going to be multiplied by 1 over the distance for the negative particle and 1 over the distance for the positive particle. You can see that the distance for the negative particle is this dashed line right here, which is basically the square root of 0.45 squared plus 0.30 squared, like that. And that's exactly the same as this one. So the two R's are really going to be the same. So let me just work that out for you, even though we really don't need it. It's going to be the square root of 0.45 squared plus 0.3 squared. Taking the square root of all that, I get 0.5408. So that'd be, in the negative case, that'd be -1 over 0.5408 meters. And in the positive case, that would be 1 over 0.5408 meters. So the electric potential is actually, anybody want to state what the answer is? Yep, it has to be 0. And that's just because of the symmetry of it. But notice how much more beautiful that is and how much easier that is than the 4-part series I did where I calculated the electric field at A and B and I calculated the electric force at A and B on a particular charge. A lot harder work, and the difference being that this was all done with scalars, whereas that other one was done with vectors. Okay. Now, your book does a really good conceptual problem, so good that I think it's best that we go ahead and cover it. So I'm going to stop sharing my screen right quick, and then I'm going to start sharing it another way, specifically with my book. So I wanted to show you this. No, I don't want that. I want to show you this particular problem and help you understand what it is. So we're looking right now at charges Q1 and Q2. This pair of charges is shown in 3 different configurations. So in configuration 1, you can see you've got a positive charge and a negative charge close to each other. Then in configuration 2, you've got the same positive charge and negative charge a little further apart. And then in configuration 3, you got 2 positive charges the same distance apart as they were in part 2. And they're asking A, which set has a positive potential energy, and B, which set has the most negative potential energy, and C, which set requires the most work to separate the charges to infinity, and assume the charges have all the same magnitude. So they called them Q1 and Q2, but we can just say the magnitude of Q1 is equal to the magnitude of Q2 is just equal to Q. Okay. So remember what the potential energy is. I'm going to write, well, I don't want to write it here, but what you can see is this particular charge and this particular charge, they're actually attracted to each other because unlike charges attract. So they're actually quite comfortable. And in fact, the configuration I is actually more comfortable than the configuration II. specifically because they're even closer to the thing that's attracting it. So the top one, configuration I, is almost like a turtle sitting directly on the ground, whereas the configuration II is like a turtle sitting on a pole that's only 1 foot tall. Okay. Now the other one is quite a bit different because the two positive charges, they actually repel each other. And that means this is like they're really, really, really a turtle on top of a really tall telephone pole. Okay. So that's the way of thinking about it. Now, when you actually go to calculate it, you know that, for instance, let's take the pink positive charge. That pink positive charge is establishing a electric potential given by Q. Let's use K because it's a lot easier to say K instead of Q over 4 pi epsilon naught. So I'm going to say the electric potential created by the pink charge in all cases is KQ over R, the distance away. The potential energy, remember, is Q times the change in voltage. And we already calculated the change in voltage in bringing a charge from infinitely far away to some distance R away. That's just KQ over R. So we're going to establish a positive KQ over R for the pink particle in all three cases. But in case I, we're going to now multiply it by a negative charge for the green charge, and the R is going to be quite small. So we are going to get a negative potential energy. And of course, a negative potential energy with a small r at the bottom means it's a very high negative potential energy. In configuration 2, it's also going to be a negative potential energy, but because the r is bigger, it's going to be a smaller negative. So in fact, when it asks which set has the positive potential energy, we can already see that it's going to be 3. But where it says which set has the most negative potential energy, it is the configuration I. Okay. Now, in the case configuration III are 3 there. In that case, we actually have KQ over R for the bigger R. And now we're going to multiply it by a positive charge. So that's going to give us a positive potential energy, but it would be about the same. It would be exactly the same magnitude as configuration II, but it's going to be positive. So which set has the positive potential energy? We already answered is III, R3. Which set has the most negative potential energy? That's I, R1. And which set requires the most work to separate charges to infinity? Remember, when we separate them to infinity, we're bringing them from what they are to infinity. So we had in case 1 a very, very big negative number. So that means it's a very, very big positive number that has to be added to make it 0. In case 2, we had a smaller negative number, which means you need to add a smaller positive number to bring it to 0. And in case 3, we actually had a small positive number. So really the one that takes the most work is the one that takes the biggest positive number to bring it to 0. And that's, of course, a case 1. So anybody have any questions on that? You can also think of it as because the positive and negative charges are attracted to one another, pulling them apart is really going to take some work because they have an affinity for one another. It's going to take more work for the second one, I mean, for the first one, because notice if you separate the first one to just as far as the second one is, then all that work done was work that you have to do in excess of orientation or configuration 2. And configuration 3, those are repelling each other. So a lot of that work's going to be done all by itself just because the nature of the Coulomb force says that 2 positive charges are going to repel. So hopefully either that mathematical description or that physical description of why the answers were what they were was helpful to you. But does anyone have any questions? Okay. I'll read you their response just so you can have some understanding of yet a third way, and maybe this will be helpful too. The potential energy equals the work required to bring the 2 charges near each other, starting at a great distance, infinity. Assume that the plus left charge is Q1 is already there, and to bring a second charge, Q2, close to the first charge from a great distance away requires external work. We know that external work is Q times V, just like we did in the previous example. So we get K, Q1, Q2 over R. That's going to be the formula for all three of them, where R is the final distance between them. Thus, the potential energy is actually equal to that work. So I get K, Q1, Q2 over R. For part A, it says we were asking which set has the positive potential energy. You can see that Q1 and Q2 both being positive is the only way that's going to be positive, or they could both be negative, but there wasn't a negative and negative configuration. So A is clearly answered by 3. Part 2, it asks which set has the most negative potential energy. You notice that both 1 and 2 have negative potential energies because they have opposite signs, but R being smaller and in the denominator makes the set 1 have the biggest negative potential energy. And then set 1, it says, will require the most work for separation to infinity, the most negative potential energy, the more work required to separate the charges and bring the potential energy up to 0. All right, so I think that should be enough regarding that one. Now I'm going to go ahead and go with our integration type problems. I'm stopping sharing and I'm going to start sharing my iPad. Again, I want to take a chance to ask anybody if they have any questions. Okay. Well, remember, folks, I'm supposed to be getting paid to help y'all learn. So if y'all don't understand something, that's on me, not on you. Of course, if you don't ask, then it becomes on you. But you guys are paying for me to be here, so it's good for you to ask questions if you have them. Don't be embarrassed. It's okay. Evidently, I forgot to cross my T on that word electric, so I just fixed it. All right. So the next problem we're going to work is something that we did before. Remember, we had a ring of charge and we calculated the electric field above it. And we got an electric field, which was quite complicated. We had to do that fancy integral that I made up for you. Remember that formula? dE is equal to 1 over 4 pi epsilon naught times the integral of dq rp minus rq in parentheses vectors divided by magnitude of rp minus rq cubed. That was a complicated formula. Now we're going to do a different one. We're going to do the same thing, but now we're calculating the electric potential, which will be a lot easier. So this is example 23-9. And with this one, what we have, I'm going to attempt to draw something nice and neat. So let's see what happens. Something like that. That's a pretty good little oval. Now I'm going to attempt to draw a coordinate system. Whoa, evidently I'm just going to put a dot on the page for no reason. And now I'm going to draw axis this way, and I'm going to draw an axis this way. This is going to be my x-axis. This is going to be my y-axis. This is going to be my z-axis. And I want to know, notice I've changed the orientation. If you're looking at the version the book does, they're doing quite a bit different orientation and stuff. I'm asking what is the electric potential at the point right above the center of the axis of rotation or the axis of symmetry. So at this point, I want to know the electric potential. Whoa, I made 2 words out of 1, or 1 word out of 2, I should say. What is the electric potential at P if the loop is uniformly charged and has a radius of R and a total charge cubed. So that's our problem. Our solution is going to require us to recall that V is equal to 1 over 4 pi epsilon naught integral dq over r. And of course, we got to remember that dq can have many forms. dq can be equal to lambda dl, which is what I'm going to use here. So I'm going to use that. Now, I know my students in general are having some difficulty understanding exactly what is lambda, exactly what is sigma, and exactly what is rho. So in this case, we have a uniformly charged ring of charge. And uniformly means that no matter what the shape is, the lambda or the rho or the sigma, they're all going to be a constant if it says the shape is uniformly charged. Okay. And using that, I can actually tell you exactly what lambda is going to be here in hopes that that will help you understand exactly what lambda is. So I'm going to say here, lambda would be, remember it's dq over dl, just like sigma is dq over dA or rho is dq over dV. In this case, it literally just reduces to q over the length of the loop. And the length of the loop, of course, is 2 pi r, and that's because this radius right here is r. Okay, so that's what we're going to actually use. And what I'm going to do is I'm going to imagine a little line coming from the origin, hitting right there. I'm going to say that angle right there is the polar coordinate theta. If I vary that by just a wee bit, then this angle right here would be d theta. That actually traces out a little arc length right here. And that little bit is dq, which is going to be lambda times the length of that little bit of arc. Now, we know S is equal to R times theta, so that means dl should equal R times d theta. So I can go ahead and write this as lambda r d theta. Now, the other thing you should see, and this might not be as clear to you if you're not one of those people that are pretty good at seeing in 3 dimensions, but you should be able to recognize that that little green line, either the one at theta or the one at theta plus d theta, doesn't matter. That little line has a length r, and in fact is specifically perpendicular to the z-axis. Now, the distance up that z-axis to the point we want to know is z. So from that, we should be able to figure out that the separation between that dq and that z is, in fact, r is equal to the square root of r squared plus z squared. So now that we have that, I can go ahead and work out the problem. I'm going to say v at P is equal to 1 over 4 pi epsilon naught. And now I'm going to integrate lambda times r times d theta over the square root of r squared plus z squared. At this point, you see we're going to be integrating with respect to theta. That has nothing to do with r squared, rz squared. So I'm now going to say the voltage at point P is equal to lambda r over 4 pi epsilon naught square root r squared plus z squared. And then all that's going to be times the integral d theta from theta equals 0 to 2 pi. Because we're going to allow that angle to go around the whole distance 2 pi. So that's going to give us lambda. The integral of d theta from 0 to 2 pi is just 2 pi. So I'm going to put the 2 pi before the r. And then down here, I'm going to have the 4 pi epsilon naught. And then the square root r squared plus z squared like that. So that is our actual electric potential, but that's in terms of lambda, which I didn't actually state in the problem, so I shouldn't do it that way. But can anybody tell me what lambda times 2 pi r is? It might help you to look at the formula for lambda that we worked out early in the problem. So lambda times 2 pi r, and notice that. Now, does anybody know what lambda times 2 pi r is?
Q.
Q, exactly. So I'm just going to write up top Q over 4 pi epsilon naught square root r squared plus z squared. And that is the voltage at point P. And that's what we were shooting for. Anybody have any questions on that one? Now, we also have this wonderful thing where, remember earlier I told you that it turns out there is a way, even though we're now working in the scalar quantity called electric potential, that theorem that I told you about mathematically that relates conservative fields and conservative forces to potentials and scalar potentials and stuff like that. From that, we know that the electric field, so I'm going to say extra. From that, we know the electric field is given by E equals the negative gradient of V. And that means specifically the gradient operator is this quantity. It's an I hat multiplied by a partial derivative with respect to X and then leave a space because it's an operator. It's meant to operate on something that you put to its right. I'll leave a space and then it'll be J hat partial with respect to Y, leave a space, and then it'll be K hat partial with respect to Z, and then all that's going to be acting on V. So you can tell the only variable in here really is the Z. So I'm going to say the electric field points only in the Z direction, and that electric field is given by E equals negative partial or negative K hat times the partial with respect to Z of Q over 4 pi epsilon naught square root r squared plus z squared, like that. So let's compute all that. I'm going to pull the negative that's out in front. I'm just going to leave it out in front, and I'm going to pull out the Q and the 4 pi epsilon naught, pull that all out in front, and then I'm going to multiply that by K hat, and then I'm going to say d by dz of specifically r squared plus z squared raised to the negative 1/2 power, because that's the easiest way to deal with it. So when I work this out, I get negative Q over 4 pi epsilon naught, all that times K hat. Now, the derivative of u to the negative 1/2 is negative 1/2 times u, which is going to be r squared plus z squared, to the negative 1/2 minus 1/2, or excuse me, negative 1/2 minus 1, which would be negative 3/2, like that, because it's 1/2 minus 2/2 is negative, or excuse me, negative 1/2 minus negative, or excuse me, minus 2/2, and negative 1 minus 2/2 is negative 3/2. And now I got to take the derivative of u with respect to z, and the derivative of r squared plus z squared with respect to z is just 2z. So what we can see is this is going to cancel out that plus, that minus to make a plus, and this 2 is going to cancel out with that 2. And finally, we can say that E is equal to QZ over 4 pi epsilon naught r squared plus z squared
to the 3/2, which if you look back in the book when we were doing the chapter on electric fields before we got to Gauss's law, so that'd been chapter 21, you would see that we got exactly this result. But you can tell this is a much, much, much easier way than what we got earlier.
Anybody have any questions with that? All right. Let's try another one. This time we're going to actually do a charged disk instead of a charged ring. Okay. And we did that one again earlier in chapter 21. So make sure you check that. Check that this matches what we got in chapter 21. So now we're going to do example 2310. Okay, so I'm going to attempt again to draw a nice smooth circular disc. So I'm going to try to keep it between these points. Actually, I think I'm going to do a little fatter than I normally do. And I think, in fact, I want it to be 4 wide, or 4 for the radius. So I'm going to say here, 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 and here. So let me attempt to draw it now. I'm going to try to draw around here. There you go. So that's a pretty decent, and that's supposed to be a circular disc, of course, but it's a circular disc that we're looking at in 3D and trying to draw in 2D. So obviously it's going to look like an ellipse. I'm going to now draw a coordinate system for us. And this, of course, is my x-axis. This, of course, is my y-axis. This is my z-axis. And this is, again, a point P at which I wish to know the electric potential. So we're asking to calculate the electric potential at P if the disk is uniformly charged and has a total charge Q and a radius R. Okay, so I'm saying this distance right here is capital R, and I'm saying the charge is Q. And again, since we said it's uniformly charged, in this case, does anybody know if we should use like a lambda or a rho or a sigma for this? Anyone? The major indicator when you're trying to decide whether you're using a sigma, a rho, or a lambda is whether it's one-dimensional, in which case you use lambda, whether it's two-dimensional, in case you probably are going to use sigma, and if it's three-dimensional, you're probably going to use rho. So I'm going to say we can tell for a fact that sigma should be equal to Q over pi r squared. So hopefully this experience with the sigmas and the lambdas and all that good stuff, hopefully that gives you some better understanding of it.
So here's our solution. Again, v is equal to 1 over 4 pi epsilon naught integral dq over r. Now you can see the integral includes in the integrand a dq into r. That variable r says if you're going to choose a differential charge element, you need to charge one such that the r doesn't differ more than more than an infinitesimal amount. Because if it did, then you'd have to find some representation of r that's done by an averaging process with, with respect to thinking about adding it all up through an integral. So the best, specifically the very best differential charge element to use would be this. I'm going to take and go a little bit less than 1 square up, and I'm going to go a little bit well, I'll go right at to 3 squares out like this. And now I'm going to attempt to draw a ellipse to represent a circle. Something like that. So that's not too bad. I really want to go a little further, so I'm going to do that. That cleans it up. And now I'm going to attempt to do another little wider on the edges, because those are we're looking at them side to, and front and back we're actually looking at it as if it's in perspective, so it should be foreshortened a little bit. So I'm going to say that this ring has a radius r, lowercase r, and therefore I'm going to call that dq, which is a little weird because there's many places, but luckily every one of those places on that dq all have the same distance r away from the point P. Notice it's going to be consistently r squared plus z squared square root. So with that in mind, I'm going to pretend like that is a length. Like if I cut that shape open, I'm going to pretend it would look like this. In other words, if I did a little cut right along this y-axis, then I could stretch that out straight and it'd look roughly like a rectangle. And of course, the inside edge would have a length of 2 pi times little r. And then this part would have a thickness of dr. So I could call it a rectangle whose area is 2 pi r dr, but in reality, what we know is it's going to have this little triangle on each end. It turns out that little triangle only differs from the 2 pi r dr by an amount that's on the order of dr squared, so we can ignore it. So I'm going to call this sigma 2 pi r dr and work it out that way. So now I'm going to say v at P is equal to 1 over 4 pi epsilon naught integral sigma 2 pi r dr over square root r squared plus oops, that should be little r squared plus z squared. So r squared plus z squared like this. Now I'm going to pull out the pi and the sigma, but I'm going to leave the 2 because it turns out that's kind of helpful. So I'm going to say sigma pi over 4 pi epsilon naught. I'm going to go ahead and cancel out this pi with that pi, and that's all good. But what I'm also going to do is I'm going to say let u equal r squared plus z squared. Therefore, du is equal to 2r dr. Now you see why I left the 2 up there. So the integral is now going to become well, actually, since the u is in the bottom, I'm going to go ahead and write it the simpler way. So I'm going to say it's u to the negative 1/2 power times du, and I'm going to integrate from r equals 0 to big R, but right now we're doing u, so that doesn't mean much. But of course, the integral of u to the negative 1/2 is u to the positive 1/2 divided by 1/2. So I'm going to get yet another factor of 2. So it's going to become 2 sigma over 4 epsilon naught times, in this case, I'm going to get the square root of r squared plus z squared, but I got to evaluate it from r equals 0 to r equals big R, which gives me v at p is equal to sigma over 2 epsilon naught times r squared plus z squared square root minus the absolute value of z, because it's the positive square root and we're letting r go to 0. And that is exactly the electric potential that we were shooting for. Now, if you take the derivative of that with respect to z, you'll get the electric field that we have found in 2. But I'm done. That is all of chapter 23. So chapter 23 has been finished. You can, of course, take the derivative to help you, but you guys are free to go. I'm going to wait till the last person leaves in case anybody has any questions, but make sure you chat me your first and last name, and thank you again. And don't forget, I did send you an email. We will be having another face-to-face test. It will definitely be available sometime next week. I just haven't decided whether I need you to get it done by Sunday of next weekend, or if I'm going to give you a couple days into it. So you need to start thinking about planning a proctor or getting someone that can help you to do the proctoring, but or making the appointment or whatever, because it's definitely going to have to be sometime during next week or possibly a couple days of the following week. So have a good weekend. Stay safe. Again, I'm waiting for the last person to leave. Thank you for coming.
Hey, Mr. Y.
Hello, Giovanni. How you doing?
I'm good. I was just wondering if you got my last text.
I replied to one about an hour or two before class, but you might have sent me one since then. You think you're going to be able to take it today?
Yes. I
Gotcha.
sent you
Yeah, I
my
see it now.
RTC. Yeah.
Okay, cool. Is that a text message that I can send your RTC person?
Yes.
ROTC, sorry. Okay, so I'll send them a message with the questionnaire. Did you want to try to take it one more time since I redid that?
I can, to see if it works.
I would say
I'll
that
just have
that
to
would save you a
fly.
little bit of trouble. Are you working again tonight?
No, I'll just have to fly home because I'm traveling tonight to
Oh,
try to
good
take.
Lord. God,
Yeah,
that's
that's why I
terrible.
was trying to take it with the proctor while I'm on campus.
Gotcha. No problem. I tell you what, don't worry about necessarily doing it tonight. You're flying today or flying tonight or flying tomorrow?
Tonight.
Okay. Just do your flying stuff. Is it possible for you to do it when you get to where you're going?
I can try. Like I just said, I just don't know if the mirror placement will be correct. Like I'll probably be in a bathroom.
Gotcha. Yeah, any way you can try to figure out to do something like that, that should probably be fine. And in fact, if you're in front of a big mirror, that would probably be pretty good. I could imagine, for instance, a scenario you sitting like on a counter in a bathroom, with the computer sitting up on, say, a box or something to be about the right height. And if you have it turned at like a 45-degree angle or something like that, then I could actually look through the big mirror and see just about everything. So that should probably be fine as well. If you want to give it a try, you can wait till tomorrow. Just let me know as soon as you do. And this time, go ahead and call me, unless it's like 3 in the morning. But if it's as late as 11:30, that should probably be fine. But you can text me that late. So just do text me or even call me to let me know that you got the message, because I don't necessarily hear when the text goes off, but I'll definitely hear a phone call. So
Okay.
let me know, and then we'll deal with the ROTC person proctoring it if it don't work again.
Okay, that works.
All right. Have a safe trip.
Thank you. Have a good one.
You too. Anybody?
Professor?
Yes.
Yes. So I tried taking the test again last night, and I tried with two different computers, different networks. Both times it was saying it was a dashboard issue.
Okay. That's the
I
problem
just
Bonnie was having.
tried.
I'm glad you told me that, because no one else had that problem. Today though,
erased that whole test, created a new one exactly the same as the old one, mind you, and then reset up the lockdown browser and monitor. So if you are willing to give it another try, it should be different now if that was something on my problem. But literally, until you just told me that, I never knew anybody else was having that problem, and I hadn't had anybody else having that problem. So I don't know what your schedule is tonight or tomorrow. Do you have any time that you could possibly try it again?
Yeah, I can try it again tonight. It won't be till like 9 or 10 again. Sorry.
Okay. Well, the same thing, if that happens in real time, go ahead and call me. Even
Okay.
if it's 10, 10:30, 11, something like that, call me and I'll see if I can come to the computer and try something else in real time when it happens. And hopefully we'll get it done. You won't have to go back and get a proctor.
Okay, sounds good. Thank you.
All right. You're welcome. See you, Evelyn.
Bye.
Carter, Hannah, you guys got questions?
I have a.
Oh.
Go ahead, Hannah.
Sorry, thanks. I was just wondering because you had mentioned possibly opening the practice test for another day if we didn't have a chance to take it, but I've been watching and it wasn't open. Where did you change your mind on
Oh,
that?
gotcha. Have you not taken the original face-to-face test?
No, I did, but I took the wrong practice test. Like
Oh,
for
that's right. Yeah, you told me that.
the wrong. Yeah, I wasn't paying.
Yeah, I completely
like
forgot you
whatever one was
said
like
that.
posted most recently and wasn't paying attention.
I know. What I'm going to do, I'm going to do it right now while you're talking to me. I have a way where I can set it where you can take it, and it'll just be for you because we knew the problem that you had. So I'm going to practice test 03. And what I'm going to do is I am going to make it available for a Miss Hannah. And until how long do you think you need?
I have a microbiome test that I'd rather focus on tonight. Do you think you can
Okay.
make it until tomorrow night?
How about I do till Sunday?
Oh, that's even better. Okay.
Okay, I'll do it till Sunday, 11:59, and I'm going to leave it open till Sunday at 11:59. Oops, that was the wrong one there. Gotcha. Oops. So that should work now.
Okay, awesome. Thank you so much.
You're welcome. You still there, Carter?
Yeah, I'm still here. I don't know if it's still recording. I was going to see if you had some time now to go over just the one question I had on the face-to-face test we've already taken.
Yes, let me turn off the recording though, because obviously some students haven't taken it.
Yeah.
Stop share for just a second. I'm going to. All right, well, that finishes that. You have a good evening, everybody. Bye-bye.